Yes, a chemical so powerful it might have been used to push rockets. Born out of secret World War II-era labs, and now showing real promise for zero-emission hydrogen power. Think drones, portable fuel cells, hydrogen storage, all powered by one small but mighty molecule.
Wait, one molecule does all that?
Sodium borohydride. Today we're putting that tiny workhorse to work in the lab.
Sodium what? Okay, slow down.
It was discovered in 1947 in a rocket propulsion lab by Hermann Schlesinger and his student Herbert C. Brown. And its crazy reduction power showed up almost by accident.
Ooh, accidental science stories are my favorite. What happened?
Brown tried to wash sodium borohydride with acetone, and suddenly isopropanol formed really fast. That observation showed it could reduce carbonyl compounds, a serendipitous moment that changed organic synthesis forever.
And Brown got a Nobel for that, right?
Yep, Herbert C. Brown earned the Nobel Prize in Chemistry in 1979. But the ripple effects kept going. Some of his students, like Akira Suzuki and Eiichi Negishi, later won the Nobel in 2010 for palladium-catalyzed cross-coupling reactions.
Those reactions are huge in making complex molecules, drugs, materials, everything. Do our students get to try one of those?
They do. Next week in lab, we'll run a Suzuki reaction. But today's focus is a hands-on reduction. We'll reduce benzophenone to benzhydrol, step by step, and show how these Nobel-winning discoveries connect to both pharmaceuticals and modern clean energy ideas.
I love that. From a splash of acetone in a propulsion lab to hydrogen storage and drug synthesis. Science really is full of plot twists.
To the round bottom flask, add stir bar, 0.5 grams of benzophenone, and 10 milliliters of methanol. Allow the reaction to stir for a moment. Lower the lab jack and place an ice bath on the stir plate, and use the lab jack to raise the ice bath around the round bottom flask. Stir for a few minutes and add 0.5 grams of sodium borohydride slowly to the reaction mixture. You will see the solution producing bubbles of hydrogen gas from the reaction of sodium borohydride with the methanol solvent. After 2 minutes, remove the ice bath and allow to stir at room temperature for 10 minutes. Again, cool the reaction with an ice bath and quench the reaction with the addition of dilute 3 molar hydrochloric acid and acidify reaction mixture to a pH of 2. Check the pH with the pH test paper until the pH is about 2. This will be evident when the pH paper turns red. If the pH paper turns blue, green, or yellow, the solution is still basic and more HCl should be added. Although it was not done here, it is recommended that you add 5 milliliters of water after adding the acid. This will dissolve the white salts in the solution and make the extraction go smoother. You may ask yourself where these salts came from and what type of salt is it. Using hydrochloric acid to quench sodium borohydride leads to the formation of sodium chloride salt, with the sodium ion coming from the sodium borohydride and the chlorine ion coming from the hydrochloric acid. After quenching the reaction, the water from the quench and acidification must be removed from the mixture so the product can be recovered and analyzed. Here the reaction mixture is being added to the separatory funnel, and the round bottom flask is rinsed with ether. Shake the separatory funnel, and being sure to vent often, and taking care to point the separatory funnel into the hood when venting. Always remove the stopper when you are not actively shaking the separatory funnel, as it will become stuck, or worse, pressure may build up inside the separatory funnel leading to the stopper popping out, or potentially the flask exploding. Drain the water, which is the lower layer, into a labeled beaker. The top layer is the organic solvent solution containing the product. This layer will be added to a flask labeled organic. After collecting this material, set it aside for a moment. Now take the water solution that you removed from the separatory funnel previously and add it back to the separatory funnel. This will be extracted with another portion of ether. The goal here is to capture all the product molecules that may have escaped into the aqueous layer. Extracting 3 times will remove 99% of the organic material from the water or aqueous layer. With each extraction, you will place the original aqueous layer back into the separatory funnel with fresh, clean, organic solvent and shake. Followed by removing the bottom aqueous layer. Remembering that this was the aqueous layer was the result of quenching the reaction with hydrochloric acid and water, and this water layer could still possibly contain some product, and this is why we are extracting it 3 times with ether. This is the second extraction. The final step of the extraction starts by adding the same aqueous layer back to the separatory funnel again. We then add clean, fresh ether to the separatory funnel. The lower layer containing the water is removed first, followed by removing the organic layer. At this point, you should have 2 flasks, one with the water layer and one with the organic layer. The organic flask with the organic layer should be a volume of twice or more than that of the water solution in the aqueous flask. This flask holds the organic material, and as you can see, there is water in the bottom of the flask forming a white bubble. To remove this water from the organic, we will wash the organic solution with water. To do this, clean out the separatory funnel and add the organic material. To the separatory funnel, add water from the tap, about 15 milliliters. Shake the separatory funnel. The lower water layer will be discarded, and the top organic layer will be dried with sodium sulfate. Dry the organic solution with sodium sulfate. Then remove the solid sodium sulfate with a Buchner funnel. Be sure to add ether to the funnel before adding the solution with the sodium sulfate. This will ensure the filter paper is adhered to the funnel and not allowing any solid to pass by the filter paper. And finally, use a steam bath to remove the organic solvent from the product. Obtain NMR and IR data.
Once the solvent has been evaporated on the steam bath, you'll be left with the chemical residue in your flask. We will now discuss how to prepare the NMR sample. For example, let's assume we have 1 gram of product in our flask. This product has a molecular weight of 184 grams per mole, and we want to prepare a 0.5 molar solution of our sample in deuterated chloroform. We will use dimensional analysis and start with 1 gram of product. Next, we will convert this into moles with a mole equivalency indicating 1 mole of product is equivalent to 184 grams of product. Next, to create a 0.5 molar solution, we use the equivalency liters per mole for molarity. Thus, we will use 1 liter of deuterate chloroform for every 0.5 moles of product, which equals 0.5 molar. Finally, we will use the equivalency 1,000 milliliters per liter to convert the units to milliliters. Solving this dimensional analysis, we get 10.6 milliliters of deuterated chloroform. This is the volume of deuterated chloroform you will add to your flask to create a solution with the proper concentration for NMR analysis. Using the graduations on the plastic pipette, measure and add approximately 10.63 milliliters of the deuterated solvent. Take care to avoid cross-contamination by ensuring the pipette never touches the flask or the compound.
One more time.
Once the sample is fully dissolved, transfer 0.75 milliliters of the solution into an NMR tube for analysis.